Yeah, so today's talk is going to be on tensor network codes of Pali code specifically. Most of the work actually predates me coming to Zurich, but anyway, maybe that's somewhat auspicious. So yeah, most of this work was done actually while I was a postdoc at the University of Sherbrooke. I'm now at Zurich. Okay, so quick overview. Today's talk I'm going to break into half a dozen sections. So first of all, I'm going to start by talking about sort of error correction in general and how what I'm going to be talking about sort of fits into the larger scheme. Let me snap over here. Oh wait, is that outside of the camera? Maybe I will stay here. Okay, well. Okay, so and then I'm going to talk about, so today I'm going to be talking about decoders, and so I'll talk a little bit about exactly what the mathematical problem you have to solve as part of a decoder is, and how that fits into something called maximum likelihood decoding. I'm then going to talk about how you can use tensor networks to do this, which is the main sort of context of this talk. I'm then going to talk about the main technical contribution of this work, which is something I call a sweep line contraction algorithm. It's an algorithm for contracting tensor networks. I'll come to exactly what that means. I'll then talk a little bit about some of the numerics that we did to actually show that this is any good as an algorithm, and then briefly go over some of the results, and then talk a little bit about conclusion and some future work. Okay. So start with error correction. As you know, most of us probably know, one of the major hurdles to practical quantum information processing, quantum computing, what have you, is the fragility of quantum states, right? I mean, I think this problem has been identified almost as long as quantum computing has existed in any real form. So there are basically two prongs to dealing with errors in quantum systems. The first is just make better qubits. Okay, that's sort of the regime that we're in at the moment. That's only so good, sort of a hardware approach. And then there's a second approach, which is essentially a software approach, using something called error correction, right? Which will, once your qubits are good enough, let you basically simulate arbitrarily good qubits, right? This is the existence of quantum error correction is really the only reason that quantum computing is even theoretically viable, right? Otherwise, you would always be chasing down error rates. So within error correction, there are sort of two major camps. The line between these is not always so clear, and it's not everything neatly fits into this, but broadly, most error correction schemes sort of fit into one of two styles, which is passive and active. So by a bit of analogy, I would sort of think of a bicycle as something that's sort of passive error correction, in the sense that as you're going down the road, there are little bumps, and your bike will bounce side to side slightly. But the gyroscopic forces, the various forces within the bike, will, in some sense, error correct this, right? You won't just straight away fall over.
Well, if you move fast enough.
If you move fast enough, yes. Interesting, I've heard there's actually a surprising amount of debate as to the classical mechanics of exactly what features of a bike stabilize it. But anyway.
But this old-fashioned bike is less stable or more stable than the new one?
I imagine it's less stable. That picture just
Yeah.
abused me. That's the only reason I included it. But yes, I think so. Yes. Yeah. So this is a system where the physics of the device is set up in such a way that it error corrects on its own, right? Whereas something like a Segway is active error correction, right? This is a inverted pendulum. This thing will fall straight away over if there's nothing going on inside of it. But it's an active error correction in that it's taking measurements about its position, about the weight of the user to adjust as it goes and keep upright. So in the end, this thing will stay upright, but for very different reasons to this. Right here, it's not the physics alone that's doing it. It's some active mechanism within it. Right. That's the sort of idea. So passive error correction. I mean, both of these are used classically, but at least for basic things like memories. Classically, passive error correction is relatively viable, right? In its simplest form, it takes magnetic cores, right? A piece of iron is essentially a self-correcting classical memory, right? That's passive error correction, right? So you see this incredibly early, I think this is from the 60s or 50s, magnetic core memory, which literally just uses little toroids of ferrite. So This, incidentally, in the background is 8 bytes, and then there's 8 gigabytes. So there's 9 orders of magnitude difference there in about 50 decades, 5 decades. So, but the point is that at the end of the day, both of these are using very similar physics internally, right, on a very different scale. But at the end of the day, they're using something like an Ising model to store information. Classically, passive error correction is relatively viable. I'm not going to go into the details, but quantumly, there's a series of no-go results that mean that this sort of passive error correction generally is considered to be a little bit too high of a bar. And so instead, most error correction work for sort of near-term applications is focused on active error correction. And this is a sort of sketch of roughly what that would look like. So you have some qubits, some quantum information, which is being affected by noise. I'm then taking some syndrome measurements. So I'm getting some information about the noise that's going on. Okay, I'm performing some measurements. And then that is fed into a classical algorithm, a decoder, which then figures out what it can about the errors, and then will apply some correction operator, right? And the hope is that this overall process maintains the lifetime of the quantum information, at least lengthens it quite significantly, right? And there are results that say that once our qubits are good enough, once the noise is below some threshold, then you can do arbitrarily, you can arbitrarily elongate the lifetime using this sort of procedure. It's this part of the sort of procedure that I'm going to be focusing on today, right? So when I say decoder, it's a classical algorithm that takes in some information about the noise, tries to figure out ideally what the noise that occurred was, and then figure out some correction procedure to apply. Okay. I should say at any point feel free to interrupt me with questions or whatever. Just, yeah. Okay. So there are many ways to measure the sort of efficacy of an error correction procedure or of a code. For the purpose of today's talk, I'm going to use a relatively crude measure, which is something called a threshold. So the basic idea is that we can think of for any given code scheme a trade-off between the or a relationship between whatever the physical underlying error rate is of my physical qubits and the so-called logical error rate of the logical qubits that I embed within that system, right? And for any given code, there's some trade-off. And for most of the codes that people consider, there are some exceptions, but certainly all the codes that I'm going to talk about today, what you see is that as you increase the size of this error correction scheme, then you get this so-called thresholding behavior, right? What you find is that below some critical error rate, this error correction procedure actually works arbitrarily well. It decreases. But then the trade-off is that above it, it actually does worse, right? Your overheads are actually swamping out whatever's going on. But you don't really care because the whole point is to operate these codes down in this regime, right? So this is the sense in which these error correction schemes can arbitrarily suppress the error rate as long as they're at least below some critical threshold, right?
And this critical threshold,
yep,
its level depends on what?
Well, so this is the key. So yeah, this point here we call the threshold. That's part of the trick is designing codes and then figuring out what their thresholds are. Generally, this is just done numerically. Exactly what they are is very tricky to say as a general rule. And the decoders that I'm going to talk about are actually really good for doing this, right? For finding thresholds of codes. It's very much dependent on whatever the code is and whatever the error process is, right? So very often codes will be designed for specific error processes. Exactly what causes the threshold is sort of quite difficult to say. For specific codes, you can relate it to there are some codes that have analytical bounds. Most of them, it's just numerical. This observation, it's quite tricky to see. Yeah. The size of the code. Yeah, that's right. So if you think of like a piece of toric code, as I grow the system size, you're going to get. I mean, this is a sketch, but roughly you're going to get curves that look like this, right? So generally what you expect is for any given physical error rate, you have an exponential suppression, and then while horizontally it varies code by code. But
so like phase transition, okay.
So actually, I'm going to show that this directly mathematically connects to a phase transition. Yes, that's right. So it's essentially a phase transition. That's right. That's right. Okay, cool. my point was that we're going to use this threshold as a admittedly somewhat crude measure of how good a code is, right? You might care, if I'm operating at finite size, I might care about more specific measures of what's going on, the finite size performance, things like this. But for today, I'm just going to focus on thresholds. Okay. So now I'm going to turn to decoding. So the main issue when you're decoding, or at least naively, is I'm trying to take some information about the error that has occurred, and I'm trying to back engineer what that error was, right? So, okay, the simplest starting point is to just ask the question, given the information that we have, which error was the most likely to have occurred, right? You like a Bayesian update backwards. So to do this, I have to start with the noise model, which is a map from errors to probabilities. For the purpose of this talk, I'm going to be looking at Pauli noise models. So the simplest example of a Pauli noise model that's most often studied is an independent noise model. So here I consider errors that are Pauli strings, and then I consider on each of my qubits, qubits, whatever, but let's say qubits. On each of my qubits, I have a local error distribution, PI, over the Paulis on that individual qubit. And then the probability of this total bit string is just the product of these local contributions, right? In fact, usually it's often considered just to be IID. So all these PIs would be the same. So independent bit flips, independent phase flips, things like this. This is by far the most studied noise model in Pauli error correction. You can actually go a little bit beyond. So I had a previous paper, which I'll mention later, looking at slightly more general models where you include spatial correlations. So this includes things like graphical models, Bayesian random network, Bayesian networks, things like this, where you now say, instead of each qubit being individually afflicted by noise, I now have some correlations, right? So maybe if one qubit has been affected by noise, the qubits around it are more likely to be hit by noise, things like this, right? But okay, you can go to more complicated models. But for today's talk, the details of this noise model don't really matter. You can just think of it as some map from my errors to some probability of that error occurring. Okay, so at least abstractly, I can think of this, as some distribution. We're considering Pauli errors, so this is discrete. So okay, I imagine there's some distribution. So now the question that I asked was, which is the most likely error to have occurred? Well, that one.
The error from this predefined set of Pauli errors. So you only consider a class of errors. Yes,
that's right. So yes, that's one important point that I'm sort of skipping over is this is all like given the information that I have, right? So I have my syndrome data that gives me some limited information. That then restricts, given that limited information, I know that it could be any of these errors, but couldn't be these errors. So I restrict to that set. And then within that, I have some set of errors that could have occurred that is consistent with the data. And they have some probabilities, right? So this error, very unlikely. I can just ignore it, right? So naively, I would just look at all these probabilities and maximize it. Now, let's ignore the issue of whether this is computationally practical for a second. So, okay, mathematically, this means that I take the maximum over all of the errors that are consistent with my data over this probability, okay? So we're done, right? Well, if this is a classical code, yeah, that basically would be it. But for quantum codes, they exhibit something known as code degeneracy.
The string, and that all the strings that connected are possible errors.
That's right. So I mean, one question you could ask is, what syndrome measurements do I do? How do I do them? Things like this, right? Which was another box in that. This I'm just assuming that you've done some syndrome measurements. I'm skipping over the issue of how do I find what errors are consistent. In case of Pauli noise, that's actually a relatively easy problem. You can there's some linear algebra to figure out generators for the set of errors that are consistent with that syndrome. So that aspect of it is sort of the easy part. I'm sort of focusing on the hard part. The hard part is this maximum that I'm going to get to, because this is over like not just generators, this is over all Pauli errors. So in these cases, it's going to be some exponentially large set.
Yes.
That's right. That's right. Even in the case of like IID noise, and I should say these error classes are determined by the code. So even if the error model was simple, the overall problem ends up being quite complicated. Yeah.
That's right. So can we continue? Okay,
Yeah.
so please go ahead.
Yeah. So yeah. So as I was saying, so in quantum codes you have this issue of degeneracy where the errors will decompose into several classes, where each of the errors within each class actually have exactly the same effect. Okay. So now the real question isn't which error was the most likely. The question is which error class. Oh, okay, skip one animation. The question is which error class was the most likely. Okay. So even if this error was the individually most likely, it seems like the probability of the rest of the things in that class actually aren't that much. So maybe this actually isn't the optimal result. So now instead we want to look at the coarse grain distribution over these error classes. What does that look like graphically? We just coarse grain this histogram, right? So now we look at, I don't care about what's going on inside the class. That's completely unobservable. I just care about the probability within each class, right? So now, previously I had said an error in here. That's not, in this case, optimal. That's actually the least likely error class in this case. And so now we rephrase it to ask, what is the most likely error class, which is now this optimization, where this E bar denotes an entire error class, right?
But this approach depends how you divide all errors into classes.
Yes, which is defined by the code. Okay. So for our purposes, that is the code, right? Yeah, that's right. Yes.
Well, yeah, just wanted to ask maybe there's some example in the Tori code here, like how the classes, like the classes would be exactly the different strings connecting to things. That's right.
So I don't actually, I did think about including that a slide on that example. So yeah, in the Tori code, for those of you who are familiar, the syndrome will correspond to the endpoints that I get. Once I fix that, the error classes are the homology classes. So whether I have a string going this way or I have a string going around the torus, those are the two different classes. And then all the perturbations of those strings, those are all of the elements within that class, right? That's right. Okay, so now we have this condition, which is called the maximum likelihood condition. For Pali codes, this, at least theoretically, this is the optimal decoding scheme, right? So if I can do this, I'm doing optimal decoding, okay? But what's the catch? Well, the catch is this probability distribution over here. These error classes, for example, in that Tori code example, are exponentially large generally, okay? So if we take these error classes, so they were defined as, I just sum up the probability of everything within that class. If we're looking at stabilizer codes, for those of you who are familiar, this corresponds to taking some representative error within that class and then summing over all of the stabilizer generators, right? So the generators actually generate these classes, they're logical cosets in group theory language of the stabilizer group, okay? So the whole point is, this is the problem. These are exponentially large sums, right? So, even if these expressions individually are nice, I have an exponential number of them that I need to add up, and then I need to do a maximization, right? That's sort of the flavor of the difficulty here. Okay. Oops. Okay. So now we move on to how we can deal with this using tensor networks. So okay. So there are many problems in physics that can be sort of thought of as, the difficulty is I have an exponential sum of relatively simple parts, right? Two that, depending on your background, two that come to mind, to me anyway, are tensor networks, which I'll come to in a second, and partition functions of stat-mech models, right? They sort of take this form, right? The individual terms are nice and simple. We have an exponentially large sum. That's the difficulty in computing them. We'll actually see in this section, all three of these things are connected. Not just like in a wishy-washy qualitative way, but actually in a quantitative way, which is quite nice. And we can actually use this for decoding. So abstractly, we might say, okay, well, we have these class probabilities, they're exponential sums. Can we maybe map them over in some sense to tensor networks? So I think the first work looking at a connection between quantum error correction and tensor networks generally was this paper by Ferris and Pauli in 2013, so almost a decade ago. Here, they weren't quite looking at this exact mapping. It was a relationship between these codes and tensor networks, but in a slightly different context. then in 2014, so the next year, there was this paper actually looking at this sort of connection from the IBM group. Here they looked at basically doing exactly this mapping, and I'll come to that in a second, but for a specific code and a specific set of error models. Right, so here they looked at the surface code, toric code, boundaries don't really matter, for bit flip, phase flip, and depolarizing. Okay, so they had a construction doing what we want, but it was for a specific code, or it was a very specific construction. But they showed that for this specific construction, it works really, really well. I think at the time, their decoder got thresholds that were state of the art, beating all other decoders, which ours is also going to do. Okay. The next step came from this paper where we weren't directly looking at, we weren't going for this tensor network connection. We're actually looking at a sort of intermediate step, which is a connection between quantum error correcting codes and StatMech models. So earlier you pointed out that this sort of looks like a phase transition. It is a phase transition in a sense, or you can directly relate it to a phase transition. So there was a series of earlier papers, Dennis Kataev, Landau Praskal, for example, again, looking at the mapping of surface codes to StatMech models. Here we actually generalized it for all stabilizer codes, actually slightly beyond that, but yeah, for our purposes, all stabilizer codes. So for example, the toric code, the surface code, actually maps over to a random bondizing model, right? And then the phase transitions of that random bondizing model directly tell you the threshold of the toric code, okay? These tend to be disordered. So when I say StatMech model, these are classical spin systems. There's nothing quantum going on here, but they are disordered systems, which makes them pretty difficult to deal with. Okay, so we showed how you can actually generalize this. And then there is a pretty standard mapping from StatMech models to tensor networks, right? So if you put these things all together, you actually get a general construction going from these class probabilities to tensor networks for general stabilizer codes. Okay, so I've been a bit vague about exactly what this means. So what this is going to look like is, so now the statement is that the class probabilities of a local Pali code, I'm exactly going to convert those into the partition functions of a local StatMech model. Again, classical spin system. Nothing too complicated. It is disordered though, I will say. And then we can go one step further and actually convert this into the contraction of a local tensor network. Okay, and now we can just sort of throw out the middle step and just think of the connection from top to bottom. One of the nice things, so I've said local here, one of the nice things is both of these mappings are in some sense locality preserving. So if we start up the top with not just a local code, but a 2D local code, then that actually propagates through quite conveniently, right? So we start with some 2D code, let's say the surface code, and we end up with some 2D tensor network. Yeah. Okay. So as I said, this previous paper where we looked at the StatMech mapping, we actually also derive, I think in an appendix, how you can actually do this general tensor network construction as well. I'm not going to go into the full construction. I will say all these things are completely constructive. They're not just existence proofs or anything. To give you a little bit of flavor of roughly what these networks are going to look like. So here is the example of the 7-qubit code. So you have 7 qubits arranged in this sort of triangle format. The stabilizers of this code exist on each of these faces. It's colored this way because this is actually an example of a larger family called the color code, which we'll talk about later, but that doesn't really matter for now. So the first step is you get, for each qubit, which are these white dots, you get a tensor in the new network. And then for each of the stabilizers, which as I said, they're on the faces, you're also going to get a tensor there as well, okay? And that sort of gives you a structure of what these look like, which is why it's locality preserving this way, right? If this was a 2D code, this is going to be a 2D code. The graph isn't exactly the same, but it's in some sense related. Okay. Okay, so now we're going to move on to the main technical contribution. Any questions, by the way?
Should there be a fourth code? I mean, corresponding to this phase. I mean,
oh wait, you mean in this? You mean?
Well, I don't know. I mean,
shouldn't there be a what?
It just looks like a projected, kind
In
of,
this case, yeah,
and
that's
you
right.
Expect another code to exist.
You mean another code corresponding to this, or?
Yes. I mean to the external vertices.
There might be. I going backwards, I haven't really thought about. Yeah. Yeah, I'm not sure. Yeah. Okay. Any other questions, by the way? Yeah.
So you have these two inequalities, right? Between
yes.
So basically, my question is: are these projections? Like, can I go from a standard model back to Pali codes, or is this like injecting one way?
Probably not, is my guess. So certainly you can go down. So the static models, you do get a specific subset of static models that have some structure to them. How much this matters, I don't know. So it might just be an overall normalization or something, not particularly interesting. My guess is no. It is actually sort of a subset in some meaningful sense. Yeah, I'm not sure. I think on the tensor network, certainly you need like the elements are all positive, for example, or something like that, because they correspond to probabilities. But to my knowledge, it's not a bijection, but it could be a bijection up to some sort of trivial equivalence. I'm not quite sure, but yeah, not to my knowledge. Yeah, that's right. Okay. Any other questions? Oh, okay. Okay. So now I'm going to move on to the sweep line contraction algorithm, which is the main technical contribution of this work. So so far I've shown you how to reduce a really hard problem to a tensor network, which is an easy problem, right? Well, so in 1D, contracting a 1D tensor network is MP. That's efficient. 1D tensor network is essentially just matrix multiplication, which is nice and efficient. I think Vaughan Jones used to describe tensor networks as like linear algebra, but not on a line. So okay, 1D, that's easy enough. 2D is easy as well, right? No, it's sharply complete. It gets really hard really quickly, and then stays that hard forever. This is even true if you impose translation invariance, periodic boundary conditions. It's uniform. The elements are 0, 1. It's rotationally. You can add a whole bunch of adjectives. This stays really hard.
What about infinite dimensions?
Well, that's just going to get harder, right? Then it's probably not even sharp. It's probably like undecidable.
Not necessarily. Like the marginal states of like infinite dimensional lattice.
Okay.
Are precisely the separable states. So
it could get easier, but I think in general it's yeah. It's probably not even sharply complete. It's probably like undecidable or something at that point. The easiest way to sort of see why this hardness sort of ramps up so quickly is that you can put graph coloring problems into a 2D tensor network, for example. Shameless self-promotion. For details, you can see my tensor network review. Anyway, so okay, these are hard. Doing some general exact contraction is not really going to be viable. These also tend to be hard even if you're trying to approximate them, right? These hardness results are quite strong. Okay, well, let's just ignore that for now. Let's just go on anyway. So 1D networks, those are really useful. Those are very practical. We can basically do whatever we want with 1D networks. And so we're going to use that. And we're going to use what you might refer to as like a dimensional reduction. We're going to use the fact that I know how to do basically whatever I want in 1D. And I'm going to try and bootstrap that up to give me a heuristic algorithm for 2D. So the 1D networks that we're going to look at are so-called matrix product states, the sort of the simplest 1D states you could think of. So for those who maybe aren't familiar with tensor network diagrams.
By the way, the hash be complete, the problem is that you can reduce any counting of P into this kind of problem.
Yeah, it's any counting problem of counting the solutions to an NP complete problem.
NP complete.
Yeah, okay. Yeah. So like so graph coloring, for example. Okay. Yeah, so graph coloring is can I color a graph in a specific way? That's NP complete. The sharp P version, the sharp coloring problem is how many colorings are there of this thing with a specific number of colors. Yes, very hard. Even just asking, is this tensor network 0 or 1, promised that it's either 0 or 1, is NP complete. Yeah. Okay, so So okay, these are the only sort of set of states that we're going to need for today's talk. So for those of you who maybe aren't familiar with tensor network diagrams, each node in this is a tensor. The shape of the node isn't going to mean anything. I'm going to use some different shapes, but it doesn't mean anything. You can just think of these as like multi-dimensional arrays. So there's like a 3-dimensional array, there's a 2-dimensional array. And then whenever I have a connected leg, that means a contraction, right? So you can think of it as like a graphical version of Einstein notation, essentially, right? So these legs being connected means that there's a contraction there. This being open means there's an open leg. So these one-dimensional states of this form are referred to as matrix product states. The name's sort of confusing because they're not matrices, they're rank 3 tensors, but anyway, that's a weird historical thing. Because they used to think of it as a vector of matrices, which I think is confusing, but whatever. Now, the relevant thing for these states is this, the dimension of these internal legs, which we call bonds. So we call these bonds, and their dimension is called the bond dimension. So now I can think of the set of matrix product states of some fixed bond dimension. And you can think of these states, if you want to think of them physically, as states with a bounded amount of entanglement, right? You can actually relate the dimension of this bond to how much entanglement this state can exhibit. So if the bonds are dimension 1, for example, this is just product states. If this is constant, then it's some bounded amount of entanglement states. And the nice thing about these is that they are a efficiently describable set of states, as long as this bond dimension is bounded, right? So n-qubit states cannot be efficiently described in general, but n-qubit states with a fixed bond dimension can. Okay. The other point is that we can manipulate these states very easily, so we can add them, multiply them, things like this, quite efficiently. Okay. So the algorithm that we're going to look at is a generalization of an algorithm that basically goes back all the way to 2004, at least in the quantum many-body systems literature, to this paper by Verstraete and Serac.
So it's not a paper from 2018. This is the old paper.
I think that's the latest version taken off the archive. It's 04.
They're updating papers after 14 years.
Yeah, I think.
Look, it's also possible they have not updated anything.
It just
they use the date it was compiled again.
Yeah, that's right. They get flushed out of the system every now and again. Yeah, I know arXiv occasionally deletes papers and recompiles them. But I think it actually was updated, but don't quote me on it. But anyway, that's So so this algorithm has been sort of floating around, and I think it actually predates this paper, to my knowledge. Although I think it came from Frank, so I'm giving the correct citation at least. The lineage of this algorithm basically goes back to this paper in 2004, where they were using this algorithm actually to look at the partition functions of quantum many-body systems. Okay, and I'll describe what their algorithm is in a second. So that algorithm was basically used pretty much unmodified in this earlier IBM paper that I mentioned. So this was bringing it to the context of error correction. It was also used in 2 follow-up papers more recently. We're getting closer to the present, by the Sydney group, the second one including me, for some other codes. But they were basically using this original algorithm unmodified, and it has some pretty significant limitations that I'm gonna come to. So, okay, what was their algorithm? Well, their idea was the following. So we start with a square grid tensor network. I'll come back to the fact that it's square grid. That's sort of going to be the limitation. I start with this square grid and I want to contract it. How do I do that? Well, the basic idea is take the left column and treat it like a matrix product state. Okay, it's rotated, but that doesn't really matter. So I think of this left column as being the thing that I have sort of in memory. And now what I'm going to do is I'm going to take the next column and I'm going to pair up these tensors and I'm going to contract them in. Okay. If you go through the details of what this contraction does, it'll actually mean that this leg in here, so this I've drawn this double line. What that denotes is that this bond dimension has now squared in size. Okay, so if you want to think of it physically, I've taken a low entanglement state and I've applied some general operator. The entanglement increases. Okay, these aren't necessarily physical states, but it's an analogy.
So double bond means that
it means that this bond dimension is squared. If I think of all the legs as the same dimension.
Two sets of indices now.
Exactly. Yeah. So I could also think of this as like a three-legged tensor, but these two are contracted the same way. Yeah. Okay. So this bond here, if I group it together, these two indices into a single index, is now squared in size. Now, if I want to do exact contraction, that's just how it is, right? This is the hardness of exact contraction coming in. I keep going, I get an exponential time algorithm. Well, I have to, I'm solving a Sharpie hard problem. That's it, right? But let's say I'm okay with a heuristic algorithm. It turns out for matrix product states, I said that 1D states we know how to manipulate really well. One of the procedures that we actually have is something called bond truncation. So this lets us take an MPS of some bond dimension and shrink it down, right? Now, you can basically think of this as compressing. Yep.
So is this basically like singular value and removing the
yes.
smallest one?
Yes, that's right. That's right. So this procedure, you can think of this like compressing. If I think of the bond dimension as a measure of how much information there is in my MPS, this is a compression procedure, but it is lossy, right? I mean, it has to be, right? So I'm basically taking, what might be a high entanglement state, at least naively, and I'm compressing it down, approximating it by a lower entanglement state. If I think of this as a physical state, which is not, but let's ignore that for the moment. Okay, so this is a heuristic. This is the step if anything's going to fail. This is the step that's going to fail. But okay, I'm just going to cross my fingers and keep going. Absorb, truncate, absorb, truncate. And then at the end of the day, I'm left with a 1D thing. Now I'm just multiplying matrices together. Okay, so I can do that efficiently. And I'm left with a single number. There's no legs here. This is just a number. That's my answer. Yep.
But after each contraction, some information gets lost. Yes?
Correct. Yeah.
Because eventually at the very end, there's no information whatever.
Yes, that's right. So yeah, so it's a controlled approximation in the sense that I get to pick the bond dimension that I lower everything down to, but it's uncontrolled in the sense that I don't really have a notion of what the overall error of this procedure is, right?
Don't control the error whatsoever.
I don't control the errors. I get to pick how crude the approximation is, but I
know how crude it is.
Exactly. So in practice, you just keep increasing the bond dimension. You hope that it sort of plateaus numerically, but you never have any guarantees. Yeah, that's right.
So it's like wishful thinking approach. You check at the very end whether it works or not.
Yeah. And it does in practice in the examples that I'm going to look at. But you almost always in tensor network algorithms, you don't really have any guarantees. I can measure how much. As Camille sort of alluded to, it comes down to these singular value truncations. I can measure how much information I throw away at each step, and then add it together, and then just like triangle inequality to give me a bound on how much my overall error is. Generally, that bound will be exponentially large. Tell you basically nothing, almost always. Unless you're really, really lucky. So, okay, in principle, you can measure it, but it's always a terrible bound. So, yeah, you don't really have any guarantees. That's the disadvantage of these methods. But as we're going to see, they tend to work really, really well. Yeah. Okay, so this square grid algorithm I described, this is essentially the algorithm from Verstrater and Serac from 2004. Basically, all of those other papers use this. Yep. Yeah.
Can I ask about this? You said that it works pretty well.
Yes.
So I imagine that if you have uncorrelated noise models and also incoherent noises like Palis, then that's probably okay, because what you're gonna throw away are those smallest values, and there's in order for error to accumulate, actually those small singular values have somehow to conspire together to make a big effect.
That's exactly the intuition. Okay. Yeah.
So then you
That's
do
right.
expect that for like correlated errors or also coherent errors, this approach may fail, or
for correlated errors, it's actually my previous paper on the StatMag mapping, we actually looked at locally correlated errors. Now, if they're non-local, all bets are off. If they're local, the expectation would be, okay, maybe I need a bit higher bond dimension, but not much higher. I'm still going to have like the local correlations in some sense. That's at least the hope, right? Is that a bulletproof argument? No, right? For one thing, I can put in the partition function of a critical Ising model and break this, right? But at least that's the intuition. And the hope is that away from the threshold, this will work. Either I'm well below the threshold, the decoding problem is relatively easy, correlations are low, etc., or I'm way above the threshold, it's just noise anyway. White noise is fine, right? Around the threshold, then it matters, right? And in practice, you see that you have to increase the bond dimension. This is all what you would expect, right? Yeah, that's right. And actually, I'm currently looking at applying this to models that aren't 2D. So you basically don't have local networks. Still works all right. We can talk about the details of that later. Yeah. Okay, so far I've just talked about this Verstrata and Serac algorithm. What's the problem, right? That seems to work fine. Everything's a square grid. I sweep over it. So this is sometimes referred to as the MPS contraction method for obvious reasons. What are the main limitations? So there are a bunch of codes that this would not really be very practical for. It's theoretically practical, but it's going to be very annoying to use. I think the main two issues with this can sort of be content into two main concerns. So the first is that previously I basically had this scheme where I'm contracting everything together column by column, right? Well, how do we define a column if I have an irregular network, right? What if my code is defined on this graph, right? What is a column? Now, you could come up with criteria for what exactly a column means, right? Well, I want to define a column to have a certain width and all this, and then I have to ask, well, is it going to be connected anymore? Maybe it gets disconnected. What about the data? I could come up with either criteria or at least some desiderata for what does a column mean now. But it's going to be annoying, and then I have to, I have to make sure that the columns actually do what I want them to do. All of this for irregular networks, that's going to be a mess, right? For a regular lattice, if I'm doing a Kagome lattice or whatever, okay, that's more straightforward. But for irregular networks, this is going to be a mess. It's possible, but it's a mess, right? The other issue is, even if we can define these, maybe I can give you some description. How do we actually find them in practice, right? Maybe I have some criteria. Maybe I can argue these columns exist. Maybe they're really annoying to actually deal with in practice, right? Ideally, I want to be able to find them algorithmically. So to give you a sense of sort of what this looks like, this is this previous paper where we did, among other things, we did tensor network decoding of the color code. The color code is defined on a hexagonal lattice. Annoyingly, you can't put it on a square lattice because of some parity constraints. And so the networks that you get at the end of the day look like this. Now, they're regular, they're based on a lattice, but they're not a square grid. And so in this paper, we had to sort of pre-process this and massage this network into this, ignoring the boundary conditions, square grid, right? We coarse-grained it in the right way. And of course, for a 2D lattice, you can show that you can always coarse-grain it into a square grid, but you sort of have to do this manually. I mean, you could imagine coming up with an algorithm. We did it in this case manually. This is annoying, right? So so David Tuckett was the one who did all the numerics on this. I don't want to take any credit. This is all good and well for the hexagonal lattice. If I turned to him the next day and said, okay, what about Kagome? He would have to go sit down and figure out how to do all this again for the Kagome lattice, right? In that sense, it's not algorithmic. You might be able to come up with an algorithm. I don't want to preclude that, but again, it's annoying. The weakness in both of these is I have this notion of columns. So one question you could ask is, can I sort of alleviate these two different concerns and get an algorithm that morally works very similar to what we had, but doesn't really need columns, right? Ideally, we would want something that's completely algorithmic. I throw a graph at it, it just runs. And I would also ideally like it to work for irregular networks, right? It doesn't need a specific lattice construction. Turns out you can do both of these, which is quite nice. And you basically get the same algorithm, or you get something that reduces to the previous algorithm for regular networks. And this relies on a algorithmic sort of paradigm that actually comes from computational geometry known as sweep line algorithms. So this is a general approach to coming up with algorithms. And the basic idea of this is to use the fact that the data that we're considering has a geometric nature to it, right? Okay, that's sort of vague, but the idea is that, well, I think this is best exemplified with a little example. Suppose I have some line segments in 2D. So this is a computational geometry problem. I have some line segments sitting in 2D, and I ask you find all the intersections, or find a intersection, or you could rephrase the problem. But let's say I want to find all the intersections between these line segments in 2D. Of course, the naive thing is just to take every pair, check, go from there. Okay, there's a naive n squared algorithm. But you might imagine, well, maybe there's some, n log n algorithm. I mean, the runtimes don't really matter too much, but maybe there's some more efficient algorithm. For one thing, whenever my algorithm is checking whether this line segment intersects with this line segment, is wasted its time, right? Like, graphically, you would sort of say, well, clearly you only check line segments that are sort of roughly close. Okay, well, what does that mean, algorithm? That's sort of vague, right? If you were to think about how a human would do this, that's exactly what they would do, right? They would see if line segments are way apart, they just ignore them. And then we sort of zoom in and start look at individual pieces, right? Is there a way to make an algorithm out of that idea? And there sort of is. So the way that you do it is you bring in the titular sweep line. So you imagine this imaginary vertical line. And what we're going to do is we're going to sweep through the data, and we're only ever going to consider parts of the data that intersect with that line, right? Because this line segment over here and that line segment over there, I can automatically throw them away and know that they don't intersect, because at no point do they vertically overlap each other. That's sort of the idea, right? So okay, what is this gonna look like? So okay, I'm sweeping through the data, and then pause it there. So at each point, I've divided the lines into 3 colors. The red lines are the lines I haven't dealt with yet. The blue lines, these are the lines I've already processed. They're done. I throw them away. I don't need to consider them anymore, right? This line segment, I never have to check whether this blue line segment touches any of these red ones, because they don't overlap vertically, at the very least, right? These green line segments, these are the line segments I have in memory. Those I'm checking intersections of. Okay, so at any given point, I'm only ever checking intersections between the green lines. And if you imagine this keeps on going, you can see only a small fraction of the lines are green at any given time, right? So I'm actually checking relatively few intersections. Okay, that's sort of the idea. Now, the details of how you update this as you're going, I've skipped over this. I have a smaller, sort of more detailed animation on my Twitter, if you're interested. But anyway, or you can ask me about it later, and I can show you. This algorithm, I should say, is called the Bentley Ottoman algorithm. There are slight modifications of this. But anyway, that gives you, I think, a general flavor of what a sweep line algorithm means, right? You have a line sweeping over the data. Generally, you're only considering data that is in some sense around the sweep line, right? What that means depends on the problem, but that's the rough idea. Okay.
So in this general scheme picture, the line is somehow, you always make it vertical and you move it right ways. So does it make sense if you somehow consider a different choice of this line? So somehow consider a different direction of sweeping. Yeah. So yeah, that's right. So it also doesn't have to move laterally. It could sort of rotate as it goes and stuff. I don't know if there's any.
To be a line like
I think that's right.
It has to be line or not?
I don't think. It could be a curve. I think it could be a curve. I mean.
Yeah, but one-dimensional curve. So you sweep.
Yeah, I don't think you get any advantage, but I think it would still in principle work, as long as it's like connected or. The direction question is an interesting one. So the point is you can flip it around. You could say, when is this going to not work very well? It's not going to work very well when all of my data is in some sense clumped into a vertical column. Right? So you imagine everything was just clumped vertically, and so everything gets included in one go. That's going to be bad. So in some sense, if all the data is sort of clumped up perpendicular to my line, it's bad. But if I go vertically, then it's really, really good, right? Generally, in practice, if you were to run this algorithm, you would start by taking your data and randomly rotating it, and then you're good, right? So
then it corresponds to, let's say, a random choice of the direction of the sweeping line.
Exactly.
The sweeping direction.
Exactly. That's right. That's right.
Good.
That's right. Yeah. So generally with these things, if the data was in some way correlated to the direction you swept across, you can get pathological cases, but you usually just assume, well, let's say I randomize it to start with, or okay, yep. Okay, so let me speed up a little bit. So the basic idea is to do something very similar. So I'm going to sweep along. So this is now my tensor network. I then take that tensor. I decompose it into an MPS. I go to my next tensor. I absorb it into the MPS, and then I restructure it, and I keep going. Okay.
So the number of vertices is preserved during this procedure?
No, not necessarily. So it can go up or down, I think. Yeah. Yeah.
I see.
Yeah.
If you start with more vertex on the.
Yeah, exactly. Yeah. So these things are always defined so that they have 3 legs, apart from the top and bottom, I have 2. These could have anything, basically. Yeah, that's right. But this is the basic idea. And you'll notice here, I don't really have a notion of columns, right? I'm just dealing with each tensor separately. But if you imagine this procedure for a lattice, it basically does the same thing as before, right? You're going to absorb in element by element, and it's going to work very similar. Okay. At the end of the day, you end up with a single number as before. Okay. So this generalizes this for Strata and Sirac algorithm, but is much more general, which is quite nice and completely algorithmic. Okay. Okay. So I don't have much time, so let me speed up a little bit for the numerics. So for the numerics, we just threw a whole bunch of codes at this because we want to prove that this technique works quite generally. So for the noise models, I'll consider the noise models and then the codes that we looked at. The first is we looked at bit flips. So you have with some probability P, you have a Pali X error occurs separately on each qubit. Independent phase flip, which is the Hadamard of that. These are in some sense sort of semi-classical errors. We also considered a fully quantum noise process, which is depolarizing, the depolarizing channel. And then, okay, I'm not going to talk about it in much detail, but actually a lot of our data also tells you about the thresholds with respect to what is sometimes referred to as the BB84 channel, which is independent X and Z errors. Right, so it's like a composition of channels of this kind.
What does it do?
So this does a Pali X with probability PX and a Pali Z with probability PZ in 2 separate rounds. Sorry?
This is X and Y.
Yeah. Yeah.
So eventually the block ball is transformed into an ellipsoid, which is not rotational symmetric.
Yes. Generally, yes. That's right. That's right. Okay. So I'm mostly just going to talk about these top 3, but actually from our data, you can actually extract information about the fourth. So most of the codes that we considered were surface codes. These are codes where you have some graph, planar graph. You have Z stabilizers sitting on the faces, X stabilizers sitting on the vertices. Now, the nice thing about these is you can define them for any graph. So we looked at the standard square graph. This is just the surface code, toric code if you change the boundary conditions. We also looked at it on some other graphs, so triangular, hexagonal. These are shown in dual pairs. Kagome and its dual, the rhombile. Truncated hexagonal and its dual, which is, at least in some cases, called the Asanoa lattice.
What is this name?
It comes from, I think it's a basket weave. It's a Japanese basket weaving term, I think. It's the same origin as Kagome, I think. Yeah, it has a really complicated tetrakiss something. I find this easier to say. Okay. And then we also looked at some random constructions. So here's a random triangulation and its dual, which is a random trivalent graph. You can also think of this, it's a random Voronoi diagram, exactly, that's right. So yeah, so actually we found this via a Delaunay triangulation, and that's a Voronoi diagram, that's right. And then we also looked at random quadrangulations and random tetravalent graphs. Okay, to skip through to the, okay. We also did some other codes to show that it wasn't just working just for the surface code. We looked at the color code and something called the subsystem surface code. This actually isn't a stabilizer code. It's a non-abelian generalization of stabilizer codes, which is sort of nice. Anyway, yeah, I'm not going to have time to talk about the details. Okay, the results. Here are all the results. The relevant details. So, okay, we have all the graphs. Here are the noise processes. Here are the observed thresholds that we got. And here are the upper bounds that are known from the Statback mapping. So these are the highest possible.
So the larger this number, the better.
Yes, that's right.
Which is the largest?
Well, so there are some codes. So what you see is you see an asymmetry. So for some codes, say on the Kagome, you have a higher phase flip threshold, but at the cost of a lower bit flip. You tend to get a trade-off between these, right? The square lattice is symmetric, obviously, because it's self-dual. And then depolarizing tends to be a bit higher. That's sort of the idea.
So is there a kind of uncertainty relation, let's say, in the product of those two numbers?
That's my next slide. That's my next slide. That's exactly right. That's exactly right. Okay, so the main takeaway here is that you can see that in basically every case, except for there's one that isn't so good. That one.
To ask a very quick question, because I know that we don't have
Yeah.
much time. How big lattice did you have to choose to get so good approximations?
Did I have to? That I don't know. I went up to 100 by 100.
Okay, 100 by
Or 100 by, yeah.
Yeah, okay.
Tens of thousands of qubits. I went up with this.
10,000 qubits.
Yeah, yeah. I probably didn't need to go that high to get these good estimates, but that's, yeah. Okay. The main interesting thing I think is this. Okay, this is highlighting these things. Okay, I sort of already did this. Okay. Okay. The nice thing is that there is this conjectured trade-off, which you've sort of, I think, already spotted, which relates to something called the zero rate hashing bound. So here are the X and Z thresholds. This is the binary entropy. It's expected that these are less than or equal to 1. In fact, the conjecture is that it saturates this for any surface code, right? So even I can vary these numbers separately, but it always saturates this inequality. I actually have some current work. This is also conjectured to be true in higher dimensions. We have some data to show this is true in 3D as well, but anyway. Here's the hashing bound. So here we're including some earlier work on a suboptimal decoder where they actually first looked at this conjecture. Here are the thresholds that they got. They don't really give error bars, so I can't tell you how big or these dots should be. But okay, it's somewhat close. It's pretty good.
This line is the entropy per one.
That's right. That's right. So this was this previous data from this Fuji paper.
All of them are very close to this boundary line.
Ours are even closer, quite a bit closer. That's right. So there it was enough to show, okay, maybe it's roughly true, but maybe it's not exactly true. And in fact, for their decoder, because their decoder is suboptimal, it's not quite true. For ours, it's within numerical precision, true. And then, okay, to quantify, okay.
It's not linear about it. It looks small.
The binary entropy. Yeah, that's right. And so I think the rather interesting thing is that the random graphs also sit on this line. So they're not really different in some sense, right? So you notice like the random triangulation, okay, it's a little bit adjusted, but in terms of this trade-off, it's just as good as a triangular graph.
So really, all error decodings, error decoders that people know, error correcting codes sit on this line.
No, this is just for the surface code, I should say.
Okay.
That's right. Well, the color code actually sits on this as well, in 2D and 3D, but not always. But it's
any analytical idea why this should happen?
No, not to my knowledge.
So
not to my knowledge.
Code is just at the diagonal.
That's right.
The same.
That's right. That's right.
So
Because
distinguish somehow.
Yeah. So the point is that like you'll notice there's a symmetry if I look at the dual.
Yeah.
It's like the triangular graph is exactly the flip of the hexagonal, and so the square grid is always going to be on that diagonal. That's right.
But in this sense, is the square? Can you consider the square pattern as the best or not quite?
In some sense, I mean, it depends whether you have biased noise.
Okay.
Right. So in a lot of, this is something the Sydney group has looked at quite a bit. There's some experimental setups where you have a lot more of one noise process than the other. Then it would actually make sense to sort of slide up this curve.
Can you artificially construct a lattice that performs much worse than the others?
Yes.
Okay.
Well, what, you mean like down here?
Yeah.
I don't know how actually. I only know how to slide up and down. Yeah. It's an interesting question whether you can purposely engineer a babble. I don't know how you would do that.
Yeah.
Actually, but you cannot do better on the word.
Yes, because if you knew how to do it in this way, then you could do it in this version.
That's right. That's right. And okay. And then you can quantify this. You can look at this entropy term. Here is all the previous ones. Pretty close to 1. In ours, it's very, very close to 1. Okay. And then I think it's just the conclusions. Okay. Okay, fine. Yeah. Here's the paper. The core, the tensor network contractor, I've also released as a Julia package. If anyone wants to use it. There's a bunch of obvious future directions, 3D codes, so codes that aren't actually local in this sense, in non-Pali noise, measurement errors, things like this. And okay, here are my socials. The talk is up there, and the source is on there. Yeah. Okay. Thanks.
Great. Thank you very much. So I appreciate your results very much, and also the way you presented, because I think it was relatively simple to understand what was it about. So, we have questions.
Yep.
Right, cool. So there's a really cool talk. Thanks.
Thanks.
So you started with this problem of computing these probabilities.
Yes.
And then reduced it to the sharpie problem.
Yep.
So can you convince me that the starting problem is sharpie half? Because
yes, I think I can. Well, okay, maybe not in a minute, but I believe there is I believe there's a paper. Okay, maybe not Sharp P, but I'm pretty sure there's a paper by actually it's probably not Sharp P, it's probably MP complete.
yeah,
There's a paper by Pauli and others, I don't quite recall, from like the late 90s, very early on, which I think they showed that decoding a stabilizer code is MP complete.
Yeah.
Now, I think that was in general. My guess would be you could restrict that to 2D, translation invariant, add a whole bunch of adjectives. That's probably still true.
Yeah.
What their proof was, presumably they reduce it to some other problem. The details I don't really know. My guess, I would strongly bet, is that would give you MP completeness.
Yeah.
I think you're right in that it wouldn't actually be Sharp P, because it's, at the end of the day, it's a discrete problem.
Yeah.
So for like the Tori code, you have 4 classes. So the answer is 2 bits. So it's not, it's going to be an MP problem is my guess, but I think that paper would give you MP completeness. If you want details, I can look it up later, but that's, yeah. Sure.
Fine. So other questions? Maybe please ask the audience.
Yeah.
He's asking, what about those non-Pauli noise? For what kind of other models of noise you could work?
Yeah, this is an interesting question. So in some sense, one of the reasons this works so nicely is it's very discrete, right? Pauli noise is discrete, Pauli noise, Pauli codes. The other is that the syndrome measurements that you do, so for Pauli codes, you do these Pauli measurements, I have Pauli errors, they're in some sense non-destructive, right? So I have some error that's occurred, I then do Pauli measurements. I'm not growing the error in any way when I do that, right? I just get some outcome. So there's never a question about whether I measure my syndromes, because it's non-destructive, I may as well. For a more general code, there's actually a question. I might have some syndromes that I could measure, but actually measuring those would potentially be destructive, right? If I have a small coherent error, then measuring syndromes will actually potentially cause it to grow, right? So there you have a lot more questions of what do I even measure to start with, right? Here, the question of what you measure is, well, you measure all the stabilizer generators. There's no question, it's non-destructive, whatever. For non-Pauli noise, it's a lot more complicated. I think the interesting thing would be stick with Pauli codes, but look at coherent noise. Maybe you come up with some heuristics about how you measure. There is very, very little work done on that. It's quite tricky. And in some sense, the worry would be that the problem might become continuous, sometimes, which might not be a problem, but it complicates it. That's the one direction I don't really have any great thoughts on at the moment, but there's a lot of people sort of working in that direction.
In principle, I was thinking you could take any model of noise and then provided you can solve those Mill-Laplante conditions.
Right.
Try to deal with it.
That would at least tell you in principle, but doing it in practice, is a very tricky thing. Yeah.
Thank you very much. So,
Yes.
last chance. What about the
That's very.
Yes,
I was wondering, like, if you could tell us more about.
Speak up.
Yeah.
Sorry, if you could tell us more about the intuition behind this hashing bound, or why it's called like this, because I sort of heard this, but I'm not so familiar with this. I guess it comes from information.
Yeah. So one thing I should say, this is referred to the hashing bound. Exactly why it's called the hashing bound. It's also sometimes known as the quantum Gilbert-Varshimov bound. It's sort of in an analogy. So it's the zero rate hashing bound. So it doesn't technically apply. So there is this, there's a thing called the hashing bound, which for finite rate codes bounds the error thresholds of those codes, but it assumes finite rate. If you just take the rate to 0, that doesn't quite work. You're commuting limits. So it's not actually, strictly speaking, necessarily a bound, right? In principle, there could be a code up here. It's just sort of named that in homage to this this bound, I think is the details. So it's not strictly speaking a bound. People get confused by this. If you want details, I would look up Gilbert-Varshimov. I think that's.
Oh, cool. Yeah, this bound I sort of know.
Yeah.
Cool. Thanks.
Okay, so let us thank the speaker again.